Welcome back, calculus fans. Today we are going to look at section 2.3 from the James Stewart calculus textbook, and we will be calculating limits using the limit laws. So we'll first talk about these limit laws. Most of them will probably seem fairly straightforward, not very surprising, and we will get past those, and then we will start evaluating limits using algebra. And this section may test your algebra a little bit, especially if you're a little bit rusty with factoring. But we are going to need to use some algebra because we're going to run into an indeterminate form, which we'll talk about quite a bit shortly. So first, let's take a look at these limit laws. And the Stewart book uses 11 of them. Other textbooks use a different number of these limit laws because some of these are built from previous laws. So for instance, when we use what we're going to call limit law number 9, it actually stems from limit law number 6. But let's take a look here, and what we've got is, first of all, c is a constant. So wherever you see c here, like this, c is a constant, like 3 or 5. That's not a variable. So c is a constant. And the limit as x approaches a of f of x, and the limit of x as x approaches a of g of x both exist. So this first law is called the sum law, and basically it says that the limit of a sum of functions turns out to be the sum of the limits. So we have this. The limit of the sums is the sum of the limits. And it just says that we don't have to combine these functions and then take the limit. We can just evaluate the limit of each of these functions and then add them. That's the sum law. Now the next one, the difference law, is very similar. Instead of adding, though, we have a subtraction. So what this says is that the limit of a difference is the difference of the limits. Then we have the constant multiple law. This basically says that the limit of this constant times a function, what we can do here to evaluate this limit, we can take this constant and move it out in front of the limit. So we can move this right out in the front here. And this is called the constant multiple law. Next up is the product law. It's probably what you would expect it to be. The limit of a product is equal to the product of the limits. And then we have the quotient law. And of course, you have to be careful here. We don't want to get division by 0. But other than that, is what you would probably expect. The limit of the quotient of functions is equal to the quotient of the limit of these functions. And this is true provided that that denominator is not equal to 0. So we need to make sure that the limit as x approaches a of g of x is not equal to 0. If it is equal to 0, then we can't use the quotient law. Now this next law, the power law, is basically we're just using the product law repeatedly. So if I use this product law and I let g of x be f of x, so it's going to be f of x times f of x, and I just use this repeatedly, I'll just end up with this power law. And this just says that I can, instead of taking the limit of this function raised to the nth power, I can take the limit of the function and raise that to the nth power. So take the limit of the function, raise that result to the nth power. That is called the power law. And then we've got what's called the constant law. This law makes sense if you think about, just think about some graph of, let's say, a constant function. So let's say this is x and this is y. Let's say we have the line y equals 2. So y equals 2. And let's say, x is just some number a here. Well, this is saying the limit as x approaches a of c is just some constant, so in this case 2. As x approaches a, nothing's happening. This is just 2. So as x approaches a, if this is a constant, it's just going to be a straight line. So the limit, in this case, the limit as x approaches a of 2 is equal to 2. Right? Because as x approaches a, you're just stuck right here at 2. So more generally, we would just say that this is equal to c. It's a constant law. And you can see this one geometrically also. If you think of the line y equals x, where x and y are the same, then the limit of this as x approaches a is just going to be essentially, you can just plug in a here and you're going to get a. Now, if you're curious, all of these can be proven using the techniques of section 2.4. And 2.4 talks about delta epsilon proofs, which used to be covered in every Calculus 1 class, but they're being covered less and less in modern times. We emphasize applied problems more. But those delta epsilon proofs are used to prove these limit laws, and you can find them in Appendix F in the book. Now, as a Calculus 1 student, we don't have to be able to prove these. This is something you would prove if you were a math major in advanced calculus, or what is sometimes called analysis or intro to analysis. I guess it'd be basically a Calculus 5 class. You take Calc 1, 2, and 3, and then you take differential equations, which I guess you could call Calculus 4, and then you take intro to analysis where the proofs come. So a student going into engineering would never take that. That would strictly be for math majors. So if you're taking the regular calculus sequence, you probably nowadays wouldn't be responsible for delta epsilon proofs, although you may talk about them a little bit. But let's get back to these limit laws so we can finish these up. So we've got limit law number 9, and this is from law 6, and also it's sort of a combination of law 6 and law 8. But basically it says that if you've got the limit as x approaches a of x raised to the nth power, we can essentially just plug in this a. So what we will get is a to the nth power. Then we've got law number 10, which says that the limit as x approaches a of the nth root of x. Again, we can just plug in that a for x, and we get the nth root of a. And if n happens to be even, if this happens to be an even number, then of course we have to assume that a is going to be greater than 0, or it'll be positive. And then the last limit law follows from law number 10, and it says that the limit as x approaches a of the nth root of a function is equal to the nth root of the limit as x approaches a of that function. And once again, we have the same caveat here. If n is even, we have to assume that this thing here will be positive, right? Because you can't have like the square root of a negative, right? We're dealing with real numbers only. So once we are aware of these limit laws, we'll typically spend a little bit of time just evaluating limits and justifying each step we take by using the limit laws. Now this is a little bit like when you first learn how to solve an equation. So for instance, think of the good old days in algebra when you're struggling to solve an equation like this, and we all first learn how to solve equations. Well, eventually you learn that you can do anything you want to one side of the equation as long as you do the same to the other side. So at some point maybe we learned names for all of these properties where we were going to use the associative property, the commutative property, the distributive property. And eventually, though, we just use these properties without ever paying attention to their names. So we would eventually learn that, we're going to subtract an x from each side here, and we would just do that. We wouldn't write down the name of the property. So think of that right here. We're going to do 2 examples where we're going to evaluate these limits. We're going to justify each step using the limit laws just so we can be familiar with them and have confidence that they work. And there'll be a couple problems in the homework where we do that. But then beyond that, we're not going to do it. So we're not going to do it anymore. So just like when you first learn algebra, maybe you're concentrating on learning names of these operations that we're using, and then eventually you just solve the equations without really even thinking of them. That's what we're going to do here. So for this example, I'm going to solve this. I'm just going to do some operations, and your job is to look at what I'm doing and justify each step that I'm doing using these limit laws. Okay, so I just did something here. I rewrote this. And so why is it that I can do this? So if you look on the previous page there, and you'll probably notice, well, it looks like I just used the quotient law, right? So I'm just going to justify each step. I'm going to justify this by writing quotient law. Okay, then from here, I'm going to go further. Okay, so when you look at this, I broke this part up, right? I took this polynomial, broke it up into two, and this one down here too. We've got this polynomial that we broke up into three pieces. And you can probably tell I used the sum law up here. And I used the sum law and the difference law in the denominator. So we've got sum law and the sum and the difference laws. So here what we did, this 2, this constant 2 I pulled out front. Same thing with this 6 I pulled out front to get here and here. And that is, of course, the constant multiple law, which I just used twice. Constant multiple law. And I used it in the numerator and also in the denominator. So I'll write it down here too, constant multiple law. Now at this point, we're ready to start evaluating some of these limits. So we can use law 9 to plug in the 2 here. This is just a constant law right here. The limit of x approaches 2 of 1 is just 1. And over here, we use law 9. Over here, we've got law 8, and then the constant law. So I can basically start to evaluate. So once we plug these in, I wrote down the laws that we used here, but now from this point on, it's just arithmetic. There's no limit laws. This is just basic arithmetic here to get our answer. So up here, we're going to have 4, so we get 2 times 4, which is 8, plus 1, which is 9. So we're going to get a 9 in the numerator. In the denominator, we've got 12 here. This is 4. So 4 plus 12 is 16. Minus 4 is 12. So you get 12 here. And I know you guys would never leave your answer like this, unreduced, right? You'd feel terrible about yourself if you did that, because you know it's much better to just reduce that to 3 over 4. So we basically taken a limit and we justified every step in the process using the limit laws. We end up with our final answer of 3 over 4. So what we'll do this one more time, just so you can get used to using these limit laws. But we're really not going to do this much. We're really, once we are comfortable with these limit laws, we're just going to evaluate the limits without ever thinking about these limit laws that we're using. So right off the bat, looking at this one, we can see we've got this root here. So look back and see, can you figure out which law we're probably going to use right off the bat here? Probably thinking the root law, right? The last one, law number 11, which is also called the root law. So we can do that. So let's do that. So this is equal to the limit as x approaches 2 of x plus 2 all under the radical. That is the root law. So now from here, you can see we've got this, the limit of this expression with 2 terms, this really small polynomial with 2 terms. So we can do the sum law to split this up. So we could write this as the limit as x approaches 2 of x plus the limit as x approaches 2 of 2. Right? We just use the sum law here. And then take a second, look back on the first page and see what law allows us to evaluate this and what law allows this. I'm going to write down the answer while you find those laws. Hopefully you saw that we can use law 8 here and then the constant law. And from here, it is just arithmetic. It is the square root of 4, which is 2. All right, the note here, this is important. Make sure you are aware. Only do this whole process. Only do this. This process of justifying each step. The process of justify each step using the limit laws. Only do this on problems number 3 and number 9 in the homework. Now, if you read the directions, you'll see that problems number 3 and number 9 ask us to justify each step using the limit laws. The problems after that don't ask us to do that, so don't waste your time doing this for all the other problems. The other problems are going to be testing your algebra as it is, so we don't need to take the time to also write these down. So, only on problems 3 and 9 do we have to justify each step using the limit laws. Beyond that, we're just going to evaluate these using algebra, which is something that we will do in just a second here. When we evaluate these using algebra, we've got a couple of theorems here that are going to make life very easy for us. We've got this first theorem. It says limits of polynomials can be found by substitution. So if this f of x, if this is just a polynomial, we've got a polynomial here, it's saying to take the limit of this polynomial as x approaches c, all we really need to do is just plug in c. It's super easy. We don't have to go through the limit laws. If you want to take the limit of a polynomial, we just plug c right in for x and evaluate it. So just to make sure we're clear on a polynomial, remember a polynomial is an expression with non-negative integer exponents. Non-negative integer exponents. So the powers have to be non-negative integers. So if you have something like, as an example, let's say 3x to the 7th plus pi x to the 4th minus 8. Okay, all we need to check is the exponents, right? Pi is not an integer, but it doesn't matter. This is a coefficient. We just need to make sure the exponents or the powers are non-negative. So this is all good. This is a polynomial. What about 6x squared minus the square root of x plus 5? Well, this one is definitely not going to work. This is not a polynomial because isn't it true that the square root of x could be written as x to the 1/2 power? So because of that, this is not a polynomial because square root of x is x to the 1/2 power. That's not an integer. Remember, integers, non-negative integers, are numbers like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, those numbers. Now, a 0, if you had a, like this is really 8 times x to the 0, right? So 0 doesn't really factor in because x to the 0 is just 1, so you just have a constant here, right? If I wrote this as 8x to the 0, it would just be still just the 8 here. So the powers just have to be non-negative integer exponents. So this is out. This one is not a polynomial. And another one that gives us trouble a little bit is like if we had something like negative the square root of 2 x to the 4th minus 1 over x. Okay, so we're looking at this. Square root of 2 is okay. It's a coefficient. We don't care about coefficients. We only care, when it comes to polynomials, we only care about the powers. The powers have to be non-negative integer exponents. So at first glance, this is clearly okay, but at first glance, this one might seem okay, but it's really not, because isn't it true that 1 over x is the same as x to the negative 1? Right? In algebra, we always learn that 1 over x is x to the negative 1. So that is not a non-negative integer power. That's a negative integer power. So that's out. Okay, so polynomials, it's just a quick review there. Polynomials are nice functions to work with. You'll see when we take derivatives and later we talk about integration, polynomials are really nice to work with. And if you have a polynomial and you want to take the limit, you don't need to worry about the limit laws. Just plug in that number. Really nice. We got another theorem that's also helpful, and this just talks about limits of rational expressions. Well, rational expressions A rational expression is like a fractional expression, and it is a polynomial divided by a polynomial. So those are also really nice to work with. And what this says is that limits of rational expressions can be found by substitution again if the limit of the denominator is not 0. So once again, just like in the previous theorem just says we can plug in the number. Right here, plug in the number. So the answer is going to be P of C divided by Q of C. And again, we have to make sure that Q of C is not equal to 0. But both of these two theorems, this one and this one, both say just plug in that number. For polynomials or rational expressions, we don't need to go through the limit laws to evaluate the limit. We can just plug in the number. Let's try one of these. The directions will say something like evaluate the limit. We've got a limit problem here. You notice this is a rational expression. So we should just, step 1, plug in the number, right? This is a rational expression. Let's plug in 1 and see what we get. If you plug in 1 for all the x's, we're going to get 1 plus 1, which is 2, minus 2, which is 0. In the bottom, we're going to get 1 minus 1, which is 0. So you always want to plug in the number with a rational expression and see what happens, because maybe we'll plug it in and we'll just get 3 over 5 and we're done. But most of the time, what we're going to get is 0 over 0. And 0 over 0 is an indeterminate form. What this means is it's not literally a 0 divided by a 0. It is the limit of a function that's approaching 0 divided by the limit of a function that's approaching 0. So we got two functions both approaching 0. And when that happens, when you get this 0 over 0, it really means that the answer to this could be literally anything. So we can't just plug in a number and get our answer. We get 0 over 0. We get what's called the indeterminate form. We get an indeterminate expression, indeterminate form. And this is the one that we'll see the most. 0 over 0, spend the most time with this. There are actually 7 of these indeterminate forms that involve infinities and zeros. I'll list them all here. We're going to get 0 over 0. We get infinity over infinity. You don't have to write these down. You'll see them as we go on in this chapter. We get 1 raised to the infinity. We get infinity raised to the 0. We get 0 raised to the 0. We get infinity minus infinity. And we get infinity times 0. These are the 7 indeterminate forms. And they are literally limits approaching these values. And what happens here is unknown until we evaluate further. So we get 0 over 0. What that means is we are unable to determine the limit just by plugging this in, because 0 over 0 could be anything. It could be anything from negative infinity all the way to infinity. So what we're going to do is we're going to use algebra to get out of this. We want to algebraically manipulate this expression somehow so that we can get out of this 0 over 0. So to do that, first we have to consider something. So I'm going to write something down and then ask you a question. Okay, so let's look what I've done. So I've started here with this expression, with this rational expression. I factored the numerator right here. All right, so I factored this, and I also factored the denominator here. I just factored an x out. There's a common factor of x here, so I factored that out. Here, now as a calculus student, we have to be really solid at factoring trinomials using either the AC method or the guess and check method or some other method you learned, but we have to be able to get from here to here. And I've been teaching calculus long enough to know that many calculus students struggle with factoring, so you're going to have to practice. It's just going to be really tough to get through a calculus class without being able to factor a trinomial. So it's okay if you're a little rusty, but you're going to want to practice. So if we do factor this, we have this expression Can I say it's equal to this expression? Is that okay to put this equal sign here? I think most of you would agree that it's okay. This is the same as this. So I'm going to erase this question mark here. And we're saying these are the same. It's just, this is just factored. If you were to graph this and graph this, the graph would look exactly the same. So once we get here, then is it okay to factor this x minus 1, this x, or to cancel this x minus 1 factor here? If I cancel this and cancel that, then can I say it's equal to this? Are these two the same? Well, at first glance, it might look like they are, but they're a little bit different. Look at this. Consider this, basically these first two. Where are these first two not defined at? You can see we can't let x be 0 because we'll get division by 0 here. We can't let x be 1 because we'll get division by 0 in that case also. So just to make a little note here, these two are not defined at x equals 1 or x equals 0, but x equals 1 is what we want to focus on. But this one, this is defined at x equals 1, right? It's okay to plug a 1 in here. So it turns out that these two expressions are not the same. They're really close, but they are definitely not equal to each other. They're not equal. If you were to graph this, expression right here, there's a hole in the graph where x is 1. Where this one, there is no hole there. So they're not equal. They're really close, but they're missing a point. So the point 1, 3, this point is not defined here. It's not defined here. So there would be a hole in the graph there. But the point 1, 3 is on this graph. So there's definitely a difference. They're really close. They are so close, but they're different. They're not the same. So that's going to be important for us. Okay, so if we just have expressions here, then these are not equal. But here's the big difference. If we're dealing with limits, say we're going to take the limit as x approaches 1. The important point is that, remember, we don't care what happens at 1. We only care what happens when we're close to 1. So if we're dealing with limits, if we take the limit of this, it is equal to the limit of this, because at that point, we never actually get to this point 1. That's going to be important for us. So if we're dealing with limits, I take the limit of this expression, it is exactly the same as the limit of this expression. So here, I can actually just cancel these factors. These cancel because with a limit, I don't actually get to 1. I don't actually get there, right? I don't care what happens at 1. I only care what happens as we're close to 1. So if there's a limit involved, these are equal. I can cancel these. Without the limit, they're not the same. With the limit, they are the same. And that's going to be important for us. So this is going to be an important point for us. And that is going to be what allows us to get out of this indeterminate form 0 over 0. We can get out of that indeterminate form algebraically as long as we're using limits. So if I go back to the original question here, I've got the limit as x approaches 1 of x squared plus x minus 2 over x squared minus x. What I can do is first, of course, I plug in 1, which we did. We get 0 over 0. It's indeterminate, which means that we have to look for a way to algebraically manipulate this somehow so that we can get it out of that form. And a lot of times, what we end up having to do is to factor the expression. So we factor it, and then we are able to cancel a term here, cancel a factor here. And then we have the limit as x approaches 1 of x plus 2 over x. Now, in this case, we plug in the 1, and then we don't have an indeterminate form anymore. Now I plug in a 1, and I'm just going to get 3 over 1, which is just 3. So the answer to that limit question, which at first was indeterminate, turns out to be 3. Now remember, indeterminate could be literally anything. So it typically won't be 3. It'll typically be something else. But in this case, the indeterminate form of 0 over 0 turned out to be a 3. The limit of this expression is 3. Okay, one more thing I need to notice, or need to mention, is this. I need this expression here. If this is not here, I can't put that equal sign. And this is something that will be a little bit of a shock sometimes for a calculus student, where when it comes to limits, we have to be careful with what we say. We have to be precise. This is a mathematical statement. So just like when you're writing a term paper in your English composition course, you can't make up words or have bad grammar. We have to start being precise at calculus level and above. So if I put this equal sign here, it has a meaning, right? So I can't leave this limit off. The limit of this is 3. It's definitely not equal to the expression here without this limit. So I need the limit here, I need it here. At this point, I'm going to take the limit. As soon as I plug in 1, there's no longer a limit. There's a limit here. Once I plug in the 1, there's no limit here. It's just 3. The answer is just 3. So I'll mention that as we go. But one of the benefits of a mathematics education is you get really focused on attention to detail, which is what you need when you're out there making the big bucks, underworked and overpaid, designing airplane wings and everything else, fiber optic systems for 911 systems. We have to be able to pay attention to detail. So it starts right here in Calc 1. So we have to be careful with our statements. We can't leave a limit off because it's no longer true without that limit, right? This is a different expression than this. Okay, so I'll mention that more as we go on here. Looking at example 4, we've got another expression here. And in this case, typically what we always want to do with the limit is just plug in 0 and see what happens. And technically, this is not a polynomial, but you see that in a little bit here, we're going to see that in almost all cases, we're going to be able to just plug in this number. So as an initial step for a limit problem, you just want to plug this in and see what happens. And in this section, it's going to be the same thing happening over and over. We're going to get the indeterminate form. But just to check it out, if you plug in a 0, so I take the limit of this expression, I plug in a 0 for h, I get 2 plus 0 under the radical, which is just the square root of 2, minus the square root of 2, which is 0 over 0. So once again, I plug in a limit, and I'm going to get our indeterminate form 0 over 0, which means that we need to manipulate this somehow algebraically. Now, last time what we did is we tried to factor. In this case, factoring isn't going to help us, but we can do something else. And there's basically, I'll just tell you, when you get 0 over 0, there are 3 things to try. 3 things. Probably in this order. The first thing to try is just see if you can factor it. The second thing, which is what we're going to see right here, is if there is a radical. If you see a radical, which we have, think of using the conjugate. Okay, we'll talk about it in just a second here. The third thing that can happen, which is what we'll see in example 5, is we can try to combine terms. Okay, so at this point, when we have a 0 over 0 indeterminate form, one of these is going to work because we have to be able to solve these algebraically. We're going to later, when we know how to take derivatives, we'll learn something called L'Hopital's rule, which makes these much easier, but we don't know calculus yet, so we have to use what we've got. What we've got so far is algebra. So with a 0 over 0 indeterminate form, try these in this order. We've seen factoring. Now we're going to see this radical. This one is kind of an easy giveaway. When you see a radical in the expression, this is probably the technique you're going to want to use. And we use this idea of a conjugate. So conjugates, a lot of times you hear of them with complex numbers. So maybe at one point you saw something like I minus 3, and you'd say, oh, the conjugate is I plus 3, right? And these have properties that when you multiply them together, nice things happen. And it's going to be, I don't want to get into complex numbers here, but we're going to see something very similar here. So what we can do is we've got the square root of 2 plus h minus the square root of 2. And what we want to do is multiply this by 1. Because we can't change the question, right? We can't change the question, so I'm going to multiply by 1. And the higher you go in math, the more often you will multiply something by 1. And the way we do this is we use this idea of a conjugate. So I'm going to change that negative to a plus. And I have to multiply, I have to make the denominator be exactly the same. Because now, I am just multiplying by 1, right? Anything divided by itself is 1. So I'm multiplying by 1. And when you do this, this will clean this up for us and allow us to get out of this indeterminate form. So to do this, though, we have to be a little bit careful. So remember what we're going to do here is we've got 2 terms times 2 terms. So we're going to have to FOIL, right? The FOIL, that acronym you learned about in algebra class, first, outside, inside, last. You usually learn about this when you're multiplying a binomial times a binomial. Well, it works here too. There's 2 terms times 2 terms, and we'll get a nice thing that will happen whenever you multiply by these conjugates, because what will happen is we'll get first times first, and then when we do outside times outside and inside times inside, they're going to cancel because one of them is going to be positive, right? One's going to be negative, and they're going to be exactly the same thing, so they'll cancel. So to do this, we just go ahead and multiply. So when we do this, first times first, we're going to get the square root of 2 plus h times the square root of 2 plus h. And what will happen there is these radicals will cancel, because just think of an example. If you have the square root of 5 times the square root of 5, isn't that going to be the square root of 25? And the square root of 25 is just 5. So what will happen whenever we do this, these radicals will essentially cancel because I'm going to have 2 plus h squared under the radical. So it works out actually nicely. So we're going to get the limit. Remember, I need that limit there. And I'm going to get first times first is 2 plus h. Now last times last, outside times outside is going to be the square root of 2 times the square root of 2 plus h, positive. Inside times inside is the exact same thing but negative, so they always cancel. So what we'll have is first times first, outside times outside, inside times inside cancel, and then we get last times last. Negative times positive is negative. Square root of 2 times the square root of 2 is just 2. So we get negative 2. Now on the bottom, what we want to do here on the bottom, whenever you're going to use a conjugate, the non-conjugate pair, which is down here, these are not conjugates. That pair, you don't want to expand this expression. I don't want to distribute this h through because we're going to be able to get something to cancel. So what I want to do is just keep it this times that. But we have to be careful. So I'm going to write this in a way that's not right. And hopefully you won't even be able to look at it. You'll be having to look away. Hopefully you're looking at that expression and you can't take it. You don't even want to look at it. It looks terrible because what I really need is a parenthesis, right? I can't just leave this off. Remember, we have to be precise in what we're writing. This is completely different than without the parentheses. Without the parentheses, it says h times this thing and then add square root of 2. But we want h times this whole expression, so I need this. Okay, so then what we've got, you can see the numerator, we can definitely clean up that numerator. So this is a limit. As h approaches 0, the numerator, 2 minus 2 cancels, so we just have h in the numerator. And we've got h times 2 plus the square root of h plus the square root of 2 in the denominator. Now you can see what we can do up here. We've got h here and h here. These will cancel. Now when it cancels, we're really dividing by h, so this becomes a 1 up here. So the h doesn't just evaporate, right? We're actually, algebraically, we're dividing, right? H goes into h one time, so this is technically a 1 down here, but it doesn't matter. But the point is, this numerator is still a numerator, it's just 1, right? So this leaves us, okay, I'm going to do something that's very wrong, and hopefully you guys won't even be able to take it. You'll be looking, saying, please, please fix this. Okay, is this true? Can I just write anything I want? No, this is absolutely not true. If this limit exists, it's going to be a number, right? This is some expression. This is not equal to a number. So I want to fix this. I need to write equals to the limit as h approaches 0. And I know it sounds picky. I know that. But we need to be precise. As a calculus student, this is where it all really starts. We have to be precise in what we're saying. Now at this point, we should be able to just take the limit. If I plug in a 0 now, so I'm going to take the limit, I'm going to let h approach 0. So basically what we're saying is that this h is getting really close to 0. So that the limiting value of the square root of 2 plus h, the limiting value is just the square root of 2. Because I can make this h be so tiny that it will have hardly any effect on the square root of 2 plus h. Right? It can make it so small that the 2 just dominates this completely. So that the limiting value of this, as this becomes really, really, really tiny, the limiting value of this is just the square root of 2. And to find that limiting value, we can just plug in this 0 here. So if I plug in that 0, I have no more limit. I'm taking the limit. I get the square root of 2 plus the square root of 2, which is equal to 1 over 2 times the square root of 2. Okay, so we've seen a couple of ways to deal with these indeterminate forms 0 over 0. And I've mentioned a few times about neatness, about attention to details, about precision, and it takes a little getting used to. So think of it like this. So let's say you're in English composition and your instructor says, okay, it's, let's get back into this. Let's get warmed up. You've been gone. Maybe it's over the weekend. So why don't you just write a little paragraph about what you did over the weekend. Let's say you write this. Okay, you write that. And you're like, hey, it's fine. Everybody knows what I'm saying. Spelling error here and there, random capital letters. Everybody knows what I'm saying. And it is true, everybody does know what you're saying, but it's not really the level of writing you would expect for a college student. It's sort of like that here. We want to get used to this precision. And the reason that it's important is, the reason I know it's important is because before I was teaching, I had quite a few jobs before I started teaching in college. So the last job I worked at was at an engineering firm, and we actually had a secretary there who had a master's degree in English, and there were a few engineers who, before they sent anything out of the office, she had to look at it first. Now, I was not one of those engineers, and they weren't terrible at writing or anything like that, but clients, if you are an engineering firm and you send out an email with a small grammatical error, those clients will lose confidence in your ability to design a system. Some of these systems are extremely expensive. They're very important. If the system goes down, it can be, people could die, for instance, if it's a 911 system, or it could be, if nothing else, extremely expensive. So if you are writing something and you make it clear that you think that these are the same thing, you are going to lose clients. Even though it has maybe nothing or very little to do with your engineering ability, we have to be careful about what we write. So the quicker you can get there, And be careful with these. I know it sounds really picky. We need these limits in here. We're putting equal signs. Just think we're writing a mathematical statement here. And it's just good practice to get used to attention to detail, because it makes a big difference when you're out of college. And I'm speaking from experience there. I've done a few jobs before I was here. I was a computer programmer. I worked in manufacturing. I worked in engineering. And in all of these places, details are really important. So might as well get a little practice now. And my nagging here and there about detail will hopefully pay off in the long run. All right, let's take a look at example 5. And we've got a limit problem, of course. And if we go to plug in the 2 just to see what happens, we're going to get 1/2 minus 1/2, which is 0. 2 minus 2, which is 0. So we get our familiar friend 0 over 0, the indeterminate form. Now in this case, this is one of the other types where the factoring isn't going to be helpful here. There is no radical, so we can't think of conjugates. In this case, you want to try to combine some terms. So in this case, maybe we could combine these two. So we can combine these two expressions and then see what happens. So to combine these, I always combine expressions using this shortcut method. So if you've got, I'll show you with a fraction. Let's say you've got 2/3 and you want to add 1/5. Well, the way we typically learn this is the longest way possible. So when we're in elementary school and we learn how to add fractions, we're taught, okay, get a common denominator of 15. So let me just kind of go through this. So we would say, we're going to rewrite this with a common denominator of 15. And then we go, well, 3 times 5 is 15, so 2 times 5 is 10. And then we have to say, okay, so 5 times 3 is 15, so 1 times 3 is 3. So we put a 3 there. And then we say, okay, now we've got a common denominator. We keep that common denominator, and then we can add the numerator. 10 plus 3 is 13, and it works, okay? It's very slow, but it works. But what is better is to use a shortcut. The shortcut way to add or subtract fractions or expressions is just to notice that if I multiply the denominators, I will get a common denominator. So I'm just going to multiply the denominators. That's going to give me a 15. That will be a common denominator. And then you multiply diagonally. 5 times 2 is 10. 3 times 1 is 3. And then I just do whatever this says. Add or subtract, I just do what it says. 10 plus 3 is 13. And so we get an answer of 13 over 15. When we first learned how to add and subtract fractions, it's good to show the getting a common denominator, of course, because that explains what's happening. But once you learn that and you're confident in it, then you should learn the shortcut. And we can use that here with these two. So we don't have to get a common denominator. Like I don't have to multiply this by x over x and this by 2 over 2. Although you can if you want to. If you're more comfortable with that, that's fine. But I'm always going to multiply expressions also using this shortcut. So if I have something like 1 over x minus 1 over 2, I'm going to do it the same way I did this. When I multiply these two together, I know I'll get a common denominator. And sometimes when you do this, like when you multiply this, maybe this is not the least common denominator. In this case it was, but sometimes it isn't. That just means you have to reduce when you're done. But this still, the technique works. So here I multiply x times 2 and I get 2x. Then multiply diagonally. 2 times 1 is 2. X times 1 is x. And then I go 2 minus x for the numerator. And you'll get that regardless of how you do it. So if you do it, you know, the traditional way where you get a common denominator and then subtract, you'll get the same thing. So either way we go, we're going to end up with the limit as x approaches 2 of 2 minus x over 2x. And on the bottom, we've got x minus 2. So we combined these terms in the numerator. We combined these terms. And now we've got a fraction divided by a fraction. Just like in elementary school when we had 2/3, I'll just stick to these same ones. Well, no, I'll use a different one. If we had 2/3 divided by I don't know, 3/7. Well, we never really divided fractions, right? What we did is we'd always multiply by the reciprocal of the second one. So you learn that this is equal to 2/3 times 7/3, right? Then we multiply, it's easy, go straight across. 2 times 7 is 14, 3 times 3 is 9. Well, we'll do something similar here. I've got a fraction divided by a fraction. And it is a fraction because I could think of x minus 2 as x minus 2 over 1. So then what we're going to do is just write that this is equal to the limit as x approaches 2 of 2 minus x over 2x. I'm going to multiply by the reciprocal. Instead of dividing, I'm going to multiply by the reciprocal, which is this. When we look at this, we can almost cancel these, just not quite. X minus 2 is not 2 minus x. But I'm just going to write in red up. I'm going to tweak this a little bit. So we can see that 2 minus x is the same as negative x plus 2, right? The x is negative, the 2 is positive. And if I were to factor a negative 1 out of here and write x minus 2, then these are equivalent, right? Because if I distribute that negative 1 through, I get negative x plus 2, which is what we've got here. So really 2 minus x is the same as x minus 2, or negative x plus 2, which is the same as negative 1 times x minus 2. So really what I've got here, I just rewrite this. Got the limit as x approaches 2 of negative x minus 2 over 2x times 1 over x minus 2. And since we have a limit here, we can cancel that, right? Those will divide out. We're left with a negative 1 here. And now we have a fraction. We can multiply straight across. We're going to get negative 1 over 2x with the limit. So this is equal to the limit as x approaches 2 of negative 1 over 2x. And now we can actually take the limit. We can plug in the 2. As soon as we can take the limit, we want to. As soon as we get out of this indeterminate form, we want to take the limit. So at this point, I'm going to take the limit. I'm going to plug in the 2 right here. We've got a rational expression. I plug in the 2, and I'm going to get negative 1 over 2 times 2, which is negative 1/4. So that is the answer to this limit question. So let's take a look at this next one, example 6. And with this one, if we just go ahead and plug in negative 1, what we end up with right here, we're going to get a 1 minus 4, which is plus 4. So we end up getting a 5 on the top. And on the bottom, we plug in negative 1, we will get negative 1 squared, which is 1, minus 3, which is plus 3. So we get 4 minus 4, which is 0. So we get, this time, 5 over 0. Now we have to be a little bit careful of this one. This is not indeterminate. Indeterminate is 0 over 0. But if we get any other constant over 0, what that means is that the limit does not exist. We can't use the quotient rule here. The quotient law, the quotient limit law doesn't apply when the limit of the denominator is 0. So the quotient law doesn't apply. So when you get a constant divided by 0, what that means is the limit does not exist. So the answer to this is this limit does not exist. D, N, E. So what's happening with this one, if you look at the graph, is if this is negative 1 right here, we've got these infinite limits. So as you approach negative 1 from the left, it's going towards infinity. As you approach negative 1 from the right, it's going towards negative infinity. But basically, if you ever go to evaluate the limit by plugging in numbers and you get a constant divided by 0, you can immediately just say does not exist. That's all you need. You don't need to make a graph. This is just, I wanted you to see the graph just so you can see what's happening with this problem. But constant over 0, we can just say the limit does not exist. For this next problem, example 7, we've seen everything that could happen so far. Remember, if you have an indeterminate form of 0 over 0, whenever you have 0 over 0, there's three things to check. Number one, see if you can factor the expression. Number two, look for a radical, and if you have a radical, look for multiply by 1 by using the conjugate. And otherwise, look to combine like terms. That's basically it. So what you should do with this problem is try this one on your own and see how far you can get, see if you can get the answer. I can just tell you ahead of time, the answer is 2/3. So give it a try and then turn the video back on when you're done. Okay, so hopefully you gave it a try. And when you look at this one, you can see that we've got a radical here. So the go-to move, I guess I should say, first what we do is we plug in the 2. And then we're going to get the 0 over 0. So plug in a 2 here. We're going to get square root of 9, which is 3, minus 3, which is 0. And then 2 minus 2 is 0. So we actually get our usual 0 over 0 indeterminate form. So then we go through our list, and there's nothing to factor here, but we have a radical. So let's try multiplying by 1 in the form of a conjugate. So the conjugate will be this same expression, but instead of minus 3, we'll go plus 3. And of course, we have to multiply it by exactly the same thing in the denominator because we need to make sure we're multiplying by 1. Then, if you remember the conjugate pair, we're going to multiply those by the FOIL method, right? And then the non-conjugate pair, we don't want to expand that. We just want to write it as this times that. So for the numerator, the conjugate pair here, I'm going to go first times first. And then when we go first times first, we end up with the square root of something times itself. So that's just going to be the limit as u approaches 2 of 4u plus 1. Right? Just like last time, the radicals will cancel. And then we know outside times outside and inside times inside will always cancel when we're multiplied by a conjugate, because we're going to get a positive 3 times the square root of 4u plus 1. And then over here, we're going to get a negative 3 times the square root of 4u plus 1. So they're going to cancel. Then finally, we'll get last times last, which is negative 3 times positive 3. Negative times positive is a negative, so we get minus 9. And then on the bottom, we're going to get, all right, I'm going to write something first and have you guys tell me if it's okay. Okay, does that look good? Hopefully you're saying no, not at all, because that is actually nothing close to what we want, right? We need these parentheses here. Otherwise, we just change the problem and we won't get the right answer. So we have these parentheses here because it is this term times this term, right? So we need these parentheses, but we don't want to expand. We only want to expand the conjugate pair. The non-conjugate pair, we just want to line them up next to each other. This thing times that thing, because what will happen is we're going to be able to cancel something in here. But if we expand it through there, if we use the FOIL method here, then we'll get just a mess, and we're not going to be able to see what we want to cancel. So up here we've got basically 4u plus 1 minus 9, so I'm just going to rewrite that. That's really just 4u minus 8. 4u minus 8. Now at first glance it looks like maybe we're stuck here, but what you might notice is there's something here, this u minus 2. We could actually factor a 4 out of this, right? If we factor that 4 out, then we'll end up with the limit as u approaches 2. In the numerator, we have 4 times u minus 2. The denominator, we have u minus 2 times the square root of 4u plus 1 plus 3. And then we can see here we can cancel these. So the u minus 2's cancel, which is good because if they're in there, we're still going to get 0 over 0. But once they cancel, then we'll be able to take the limit. So we get the limit as u approaches 2, 4 on top, 4u plus 1 plus 3. So we take the limit here. We plug in the 2. So plug in a 2 here, and we're going to get the square root of 9, which is 3. So we get 4 over 3 plus 3, which is 6, or 2 over 3. So we get 2/3 as our final answer. This problem, by the way, is number 22 in the book from this section, section 2.3. All right, looking at example 8 here. We can see if I plug in a -1, I'm going to get 1 minus 2, which is minus 1, plus 1, which is 0, then -1 to the 4th power, which is going to be 1 minus 1, which is 0. So we get our familiar indeterminate form of 0 over 0. So what we could do, maybe try to factor here. Now this one, if you remember the good old days in algebra, you'll probably remember something called the difference of squares, or the difference of perfect squares. It's got to be a difference of a perfect square and another perfect square. And these are both perfect squares because the square root of x to the 4th is just x squared. The square root of 1 is just 1. So we can definitely rewrite this. We could rewrite this as a limit as x approaches -1. And on the bottom, if you remember the difference of perfect squares, what we do is we write it like this. And we basically go, okay, the square root of this one goes here and here. So that means we're going to put x squared and x squared. Then the square root of this one goes here and here. The square root of 1, of course, is 1, so that goes here and here. And then we put a plus and a minus, or a minus and a plus, it doesn't matter. And you can check this if you FOIL these two binomials together, you get back here because outside and inside end up canceling. So as far as the bottom goes, we could factor that. X squared plus 1, x squared minus 1. And the numerator also factors. So if you play around with this one, you'll see if we go x and x, 1 and 1, both of these are the same. Okay, so far, it looks like we are still stuck here. Because remember, we can't do anything weird like cancel these x's, because this is a whole factor, right? Factors cancel. But what you might notice is we've still got something that can factor here. This is still a difference of perfect squares. Right? This is a sum of perfect squares, which doesn't factor across the real number system. We need complex numbers here, and we don't use complex numbers in calculus, or at least not very often, and we're not going to be using them. So we can just factor the denominator. Again, it's perfect difference of perfect squares. So we've got the limit as x approaches -1. Numerator stays the same. The x squared plus 1 stays the same. But x squared minus 1, we can write as x plus 1, x minus 1. Right, and if you're not sure, just FOIL this, and you'll see you'll get back here. But this does allow us to cancel. So the x plus 1 terms will now cancel. So we can rewrite this as the limit as x approaches -1 of x plus 1 over x squared plus 1 times x minus 1. All right, so now let's see if we can take the limit. We plug in -1 up here, we get a 0 on top. Now, if we get a 0 on the bottom, it's still indeterminate, right? If that happens, it's still an indeterminate form, so we're going to have to do something else. But if we plug in -1 in here, we get -1 squared, that's 1. 1 plus 1 is 2. So we got a 2 here. Then here when we plug in -1, I get -1 minus 1, which is -2. So we've got 2 times -2. Well, that's just 0 over -4. But 0 over -4 is 0, right? if you got a fraction and the numerator is 0, we're okay. 0 divided by a number is just 0. Now the problem we had before was 5 divided by 0, which is undefined. So these are completely different here. 0 over -4 is okay. Just means the limit of this is 0. So if we look at this expression and we plug in numbers really close to -1, this thing's going to get closer and closer and closer to 0. And sometimes students get these mixed up. So let me show you a really easy little memory hook here. Okay, I'll use 5 over 0 and 0 over 5. Okay, let's compare these two situations. Okay, let's look at this one first. So let's say you have $0 and you are willing to divide it equally amongst your 5 friends. How much are they each going to get? $0, right? Okay, but let's consider this other case. Think how sad this is. You got $5 and you are willing to divide it equally amongst your no friends? That is not going to happen. That does not exist. Everyone has at least one friend, right? So 0 divided by 5 is just 0. We can divide 0 into 5 parts. They're just all 0. But this one we just can't do. We can't divide something into 0 parts, right? So 5 over 0 does not exist. 0 over 5 is 0. So when you take a limit and you get a 0 in the numerator and a non-zero in the denominator, it's just 0. That's okay. All right, so hopefully that will help. And let's move on to example 9. So this one, if we plug in a -1, can you guess what's going to happen? I'm guessing we're going to get 0 over 0, the indeterminate form. And in fact, if you check, you will see that when you plug in -1, you're going to get a 0 on the top and a 0 on the bottom. So why don't you turn the video off and see what you can come up with here. We need to come up with an answer, and I can tell you just for checking purposes, the answer should be 1/4. So give it a try and then check back. Okay, so hopefully what you did is you saw, well, there's no radical here, there's nothing to combine, so it looks like we are going to have to factor. Remember, that's all we've got. The only tools we've got right now are algebra. So these have to be able to factor. And if you play around with these enough, do the AC method or the guess and check method or whatever your favorite method is, you'll see that these do factor. And luckily for us, they factor in a way where we're going to be able to get something to cancel. Because right now, if I plug in -1, I'm going to get 0 over 0. But we can see we've got this factor of x plus 1 that will cancel. And once we do that, then we're going to get a problem that we can evaluate. So we're going to get 2x plus 1 over x minus 3. And now I can take the limit. I plug in a -1 into the numerator, and I'm going to get -2 plus 1, which is -1. Plug in -1 in the denominator, I get -1 minus 3, which is -4. And I know you guys would never leave an answer like that, right? An answer like this, you would never do that to me, right? When I'm grading papers and I see that, oh boy, it makes me reach for the whiskey. So if you care about my liver and kidneys, please never do that. We know that a negative divided by negative is a positive. So we want to write 1/4. Or for the decimal fans out there, I know some of you do not like fractions, you could write 0.25. Both of those are just fine. But we don't want -1 over -4. All right, so hopefully those made sense. Those are the kind of problems you're going to see a lot. So remember, when you get 0 over 0 in this section, which you will see all day long, think, okay, can I factor? If not, look for a radical. If there's a radical, think of a conjugate. Again, these are for 0 over 0, this indeterminate form. First look for factoring, then look for a radical, and then finally see if you can combine like terms. And one of those three has got to work because we just don't have that many tools at our disposal right now. We just have algebra. And there's another thing that we'll see, something, well, it's a theorem called the squeeze theorem, sometimes the sandwich theorem or the pinch theorem. All of these names are perfect names for this theorem. And we'll see it from time to time in Calc 1, maybe even a little bit in Calc 2. And it looks like this. It says, when we've got this function f of x, which is less than or equal to g of x, which in turn is less than or equal to h of x, or in other words, g of x is in between these two. When g of x is in between these two. When this is true when x is near a, except possibly at a, remember we don't really care what happens at a when it comes to limits. And also, the limit as x approaches a of f of x, this function, is equal to the limit as x approaches a of h of x, this function. So these two here, when they equal some number L, remember L is always going to be a number, then what will happen is the limit as x approaches a of g of x, the function that's in the middle of those two, will also have to equal L. With this picture, it's easy to see this. So we've got the way this is set up, h of x is greater than g of x, which is greater than f of x. So h of x is on top, here's g of x and f of x. It tells us that as x approaches a, the limit of f of x and the limit of h of x are both L. So approaching a, f of x and h of x from either side are L, and g of x is stuck in between them, so it gets squished in between them. So it gets squeezed or sandwiched or pinched. You can imagine like fingers here pinching these all three together. So this middle one also is L. And as a Calc 1 student, we'll see this in questions like this. It says, to prove that the limit as x approaches 0 of x squared times the sine of 1 over x squared equals 0. And it'll typically happen with something like this where we've got this function here, or this piece of this x squared piece, as x goes to 0, x squared goes to 0. So it's sort of like a 0 times. Then over here, we know that the sine function oscillates forever. And so if you think about the argument here, or the input to the sine function, as x gets smaller and smaller, this number just gets bigger and bigger. When you think of a sine curve, all that means is we are going further and further out, but nothing changes in the sine function, right? It just oscillates forever, never approaches any one number. So that this limit here actually by itself, without the x squared, this limit does not exist because it doesn't ever approach any one number, and this one's 0. But we have a combination of these two. So in a case like this, you can see this coming a long ways away. The question will be, prove this particular limit equals 0. And as a Calc 1 student, when we use the squeeze theorem, there's going to be a sine or a cosine in here. Now, when you see why, we'll see how to do this when you'll understand the sine or the cosine. So we'll have some like this. They want us to prove that the limit of this function is 0, and we end up proving it using this squeeze theorem. All right, so let's see how we can prove this. First, we have to start off with this sine function. So I'll start with a little note here. Let's have this little note. -1 is less than or equal to the sine of any argument at all, including 1 over x squared, which is then less than or equal to 1. We know this is true because this is a sine of something. Think of the sine graph. It's locked between -1 and 1, right? Sine and cosine both have a range from -1 to 1. So it doesn't matter what I plug in here. The result, the sine of whatever this is, will be stuck between -1 and 1. So we can say this for sure. And also, we know that as x approaches 0, and I plug numbers in here and square them, it doesn't matter positive or negative. Whatever I plug in here, I'm squaring it. So x squared is going to be greater than 0. Right? Remember, I never get to 0. I get infinitely close, but I don't ever get to 0. So x squared in this case is always going to be a positive number. Always positive because I'm plugging in some number close to 0, but not 0, and squaring it. So positive or negative doesn't matter. When I square it, it's positive. So because of that, I can multiply this compound inequality, all three parts of it by x squared, and I don't have to worry about reversing the sign. So if you remember back in the good old days of algebra class, you'd be solving an inequality like this, and you'd have negative 3x is less than 6, and you try to solve this inequality, so you'd say, well, I need to divide by a negative 3. And then we were all taught that when you divide by a negative, we have to reverse the direction of the inequality. So this becomes x is greater than negative 2. And it turns out that whenever you have an inequality, if you multiply or divide by negative, this has to happen. So here, I'm multiplying all three parts of this compound inequality by x squared, and I know that I do not have to reverse direction because I know that x squared is going to be positive. So I end up with this new compound inequality. I'll multiply all three parts by x squared. I don't have to change the direction of the inequalities because I know that x squared is going to be greater than 0. So from here, I'm going to end up using the squeeze theorem. So we've got three parts here. We've got this negative x squared. We've got x squared times the sine of 1 over x squared, and we've got x squared. Okay, so what we can do is take the limit as x approaches 0 of negative x squared. Now, I know I can just plug that in, right? This is a polynomial. We've got that theorem that says we can just, if we're evaluating the limit of a polynomial, we can just plug in the number, and whatever we get, that is the limit of this. So I plug in 0, get negative 0 squared, which is 0. So this part of it goes to 0. Now I'm going to take the limit of this other part here. Limit as x approaches 0 of x squared. Well, that's also going to be equal to 0. So I know that this thing, this x squared times the sine of 1 over x squared, is stuck between negative x squared and x squared. And if I take the limit as x approaches 0 of this thing, it goes to 0. This thing also goes to 0. So by the squeeze theorem, this also must go to 0. So I could say, therefore, this symbol here, it means therefore, and you'll see it in calculus and in higher and in arguments. So whenever you see this, it just means, looking at this, I make a statement here. Because of this statement, I can say this next thing. So I can say, therefore, the limit as x approaches 0 of x squared times the sine of 1 over x squared also equals 0 by the squeeze theorem. So you will have a couple of them like that you can try. Also, I should probably show you something you might see. Sometimes, this isn't really a super great proof or anything, but sometimes at the end of a proof, I guess if we could consider this a proof, you'll see this QED. You'll see this in math. And it's a Latin phrase that means that which was to be shown. Something like quod erat demonstrandum, something like that. But it means that which was to be shown. Sometimes you even see a little box at the end of a proof, sort of a symbol that means the same thing. But if you're kind of a hip mathematician, then you might see FS. That means faux shizzle, but only do that if you're super cool. Also, only do that in this class. I'm not sure that one's quite understood everywhere. But you'll have probably have a couple of them like that, where we had to do a proof using the squeeze theorem. And then one last one we should look at. And after you've seen this one, you'll be ready for anything you're going to run into in the homework. But of course, all the learning takes place in the homework. When you watch these thrilling videos, really all you will learn, you'll learn the basic ideas, but the real learning takes place when you are doing it on your own and you go through all the speed bumps that we all go through along the way. So homework is super important. You can't just watch these videos. Just like I can't just watch somebody play in the NBA playoffs and think that I'm going to go out for the team, right? It is exactly the same way with calculus. We have to practice. So let's take a look at this very last problem. This one is actually number 42 in the book. This one, you'll notice it has an absolute value. So we're going to have to deal with this absolute value. And in calculus, we almost always want to avoid absolute values because we'll find out later that absolute value functions are not differentiable at the points. So we typically want to get rid of them in calculus. So we've got something that we'll see quite a bit in calculus, and it looks like this. It's the absolute value function. And this is actually a piecewise defined function. So the absolute value of x is equal to x if x is greater than or equal to 0, and it's equal to negative x if x is less than 0. Now, when we were young and we learned about absolute value, our teacher would say something like, okay, we've got the absolute value of negative 4, and we'd learn, well, it's just going to be a positive number, so it's going to be 4. And if we had the absolute value of, let's say, 7, it's still going to be positive, it's just going to be 7. So we learned it like that. Now, technically, this is what we were doing, because if you plug in negative 4 in here, you'll see that if I use a negative 4, the answer to this is going to be the opposite of the input because I'm down here. Negative 4 is less than 0, so I'm on this branch. So I get whatever x is, I get the negative x. So it would be like negative 4, which is 4. Well, until calculus, we don't need this bulky definition. The way we did it in elementary school is just fine. It works great. But in calculus, because there's going to be different inputs that can be here for this x, we need this definition. So what we'll do from time to time in calculus is we will use this basic definition here. So we use this definition to model the absolute value that we need. So the absolute value that we need is the absolute value of x plus 6. But I'm going to write it down here and I'm going to model it based on this one. So for the absolute value of x plus 6, it's going to be x plus 6 if x plus 6 is greater than or equal to 0. Now this means if I solve this inequality for x, I'm just going to subtract 6 from each side. So what that implies is that x is greater than or equal to negative 6. Then on the bottom part, just like we did here, the absolute value of x plus 6 is going to be the opposite of x plus 6. So this will be minus x plus 6 if x plus 6 is less than 0, or in other words, x is less than negative 6. Then we just have to break this up into two pieces based on whether we are here or here. So to get started with this limit, as x approaches negative 6, let's assume that we are greater than negative 6. Now, we don't really need to worry about the equals to because it's a limit. We never care about what happens at negative 6. So we're either going to be greater than negative 6, meaning we're approaching it from the right, or we're going to be less than negative 6. So when there's an absolute value here, we just have to consider approaching from each side because when our numbers are greater than negative 6, we're going to be on this branch where these are equal. But if x is less than negative 6, when we're approaching negative 6 from the left, then we're going to be in the case where the absolute value of x plus 6 is the opposite of this. Remember, for this limit to exist, it needs to exist on both sides. And it's really not always an issue, but it can be an issue with this absolute value here. So what we're going to do is just break this into two parts. And that will typically be what we do all the time in calculus with an absolute value. We break it up into pieces. So to get started with this one, let's say if x is greater than negative 6. Okay, so we're on this branch. Again, I don't have to worry about it being equal to. This is greater than or equal to negative 6. It's never going to equal negative 6 because it's a limit. We don't care what happens at negative 6. So if x is greater than negative 6. So in other words, what we've got a number line here. And we've got, let's say, negative 7, negative 6, negative 5, right? So there's a 0 here. If x is greater than negative 6, so we are over here, greater than negative 6, we're coming in from the right. So we are over here, these numbers greater than negative 6, we're approaching negative 6 from the right. So in that case, what we're going to have is the limit as x approaches negative 6 from the right of 2x plus 12 over the absolute value of x plus 6. Well, we are approaching it from the right. Well, from the right, it means that x is greater than negative 6, so that this absolute value of x plus 6 is the same as x plus 6. These are the same. So I could rewrite this. You could say this is equal to the limit as x approaches negative 6 from the right, 2x plus 12 over x plus 6. And I already messed that up. I don't need the absolute value there. I just need x plus 6, right? Because we just said absolute value of x plus 6 is x plus 6 if x is greater than or equal to negative 6, which it is because we're coming in from the right. And then you can see this numerator, 2x plus 12, we can rewrite that. That's just the same as the limit as x approaches negative 6 from the right of 2 times x plus 6 over x plus 6, which then we can get these to cancel. And that will give us the limit as x approaches negative 6 from the right of 2. Well, now I've just got the limit of a constant, which is just the constant. So that answer is 2. So when we are approaching from the right, the limit is 2. So what we have to do now is just see if we approach from the left, will we get the same thing? So let's consider that. What about if x is less than negative 6? So x is less than negative 6. So now on the number line, up here, x is less than negative 6. So we're coming in from here. We're coming in from the left. So in this case, we are coming in here. We're approaching negative 6 from the left. So we'll have the limit as x approaches negative 6 from the left of 2x plus 12 over the absolute value of x plus 6. These numbers are all less than negative 6 because they have a larger magnitude and they're negative, right? So they're going to be less than negative 6. So here, now we're over here, x is less than negative 6. We're on this branch. On this branch, the absolute value of x plus 6 equals negative x plus 6. So we can swap these out. So I can rewrite this limit as the limit as x approaches negative 6 from the left, 2x plus 12 over negative x plus 6. And then just like before, we can factor the numerator. We'll get 2 times x plus 6 over negative x plus 6. And just like before, we can cancel here. And we're going to get the limit as x approaches negative 6 from the left of negative 2 this time. And that equals negative 2. So we approach from the right, we get 2. We approach from the left, we get negative 2. They're not the same. So we know what that means, right? If the left-hand limit does not equal the right-hand limit, the limit doesn't exist. So because of that, the limit as x approaches negative 6 of 2x plus 12 over the absolute value of x plus 6, absolute value of x plus 6 does not exist because the left-hand limit is not equal to the right-hand limit. Okay, so I think you've seen everything you're going to need to get started, and now we just have to get at the homework, give it a try, and let me know if you have any questions.